I will present our project, which is on software security for the IoT. IoT is now the infrastructure of our society, among other things. So, of course, security is a very important concern. Our project focuses on security of the software on IoT, software that can run on IoT platforms, in IoT protocols, in IoT applications. On top of regular security challenges, IoT systems have challenges such as these systems have a large attack surface. You can even carry them away. You can access them over the internet or on the wireless interface. And they have typically at least the smaller parts, very small resources, meaning that normal security services are typically not available on them. So that motivates the directions for the project. So we work on software security in IoT nodes, meaning checking for vulnerabilities, bugs, or making sure that they don't exist. Similarly, for robustness of protocols in IoT systems. We also focus on mechanisms for protecting the nodes in IoT systems. Nodes can have very small batteries or even be battery-free. So you can just carry them away. What do you do? Even small nodes can have now support for trusted execution environments. They are appearing. But typically, they are very small, and we need to see how to equip them with more functionality than they have at present. The project is a collaboration between researchers at Uppsala University, groups working on verification and testing, and programming language technology, and groups at Kista. There is the network wireless networking group with Timo Voigt, Luca Mokkola. They were behind the development of the Kontiki operating system, and the security lab headed by Shahid Raza, whom you heard this morning. We have a reference group of SMEs working with software on IoT. This is the homepage. You can find most of our material there. Let me now give you some glimpses of work we have done and published in the last year since the previous CyberNode meeting. So one thing we did was in the area of software security for IoT nodes, was to work on testing to check for vulnerabilities or bugs. And this area has seen a very rapid and even very surprising research progress in the last decade, stemming in large part from the development of fuzzing techniques. Some of them are mainly so-called gray box fuzzing, are successful because you can, with small intelligence and a large number of test cases, you can quickly or find deep bugs in many software systems. Other techniques are more clever and can find hard to find bugs, but take more time. These two techniques are, in some sense, complementary. So hybrid fuzzers try to combine them. And what we are doing is to see how these techniques can be adapted and be evaluated on software for IoT. So one thing we did was to create infrastructure for using these fuzzers on IoT software, in particular, the Kontiki NG network stack. And we evaluated a large number of state-of-the-art fuzzers and also checked how they perform in combination with instrumentation using sanitizers to check for, say, memory problems. And we have reported the experiences and also shown the effectiveness of these tools by detecting a large number of vulnerabilities that have been reported, resulting in CVEs and many bug fixes. In the area of security protocols, where we use mainly testing, we face the problem in security testing that the first type of testing for protocols is for interoperability, meaning you test the protocol in a friendly environment. For security protocols, you also need to check that adversaries cannot make problems by sending malicious data or malicious packets. One thing you need to check is that, which is on top of normal software security, is that when you send a sequence of packets, that you cannot fool an implementation by sending a sequence of packets that omits stuff or reorders stuff and confuses an implementation. So to take an example, on the right, we have DTLS, which is one of the main security protocols for IoT. When you want to establish a secure session, you have to exchange a sequence of messages that are carefully ordered in this way. And an implementation of, say, a server in DTLS has to check this order carefully in order not to be fooled into accepting insecure connections. So how do you now check that an adversary cannot reorder, omit, or duplicate messages and fool DTLS servers if you just want to test it in a black box fashion? Well, we have developed a technique called state fuzzing, where you test this implementation for some carefully selected test sequences. Then you can construct a model from the information you learn. This model, in some sense, captures the reaction to all possible input sequences of packets. And then you can inspect this model by checking requirements on it. All this is fully automatic. And we have applied this to a number of security protocols in IoT and published it in a top, it will be published in a top security conference this year. Of course, you also want to check the data handling. This is a bit similar to testing software, but we have to adapt it also to the situation in protocols where you have to check the reaction to a sequence of data being sent. And here, the techniques that are successful also for software fuzzing, we are adapting them to protocol testing. One is symbolic execution, which we have applied to DTLS and Quick and found a number of bugs. The effectiveness of our work and our techniques are shown by the detection of a large number of vulnerabilities, bugs, and resulting in a number of CVEs. We have also produced on the fly a number of open source tools. They are available from our homepage, and you can use them wherever you find them convenient. Concerning runtime mechanisms, we have work on trusted execution environments that were the topic of previous talks. So they provide protected environments for special mechanisms such as secure boot, authentication, etc. Now they have been around on major platforms for a while. On small platforms, they are only now appearing. And we have looked at one such technology, Trust Zone M, on small devices. And on them, they still lack some functionality that you can see in larger systems, such as authentication of communication requests from untrusted applications, or detecting if some application inside this secure world has been compromised. We are also in progress of supporting trusted execution environments, in particular Trust Zone M, in Contiki NG. Finally, a word on low-energy computing, which we now term as the field of intermittent computing, because with almost battery-free devices, you have to let them operate in a mode where they charge for a while, then compute for a while, then charge for a while, then compute for a while. And specific security problems occur because when they are suspended, you have to store the persistent state and use it resilient to tampering. So how do you do that? We have compared different schemes. Another new area of security problems is in so-called energy attacks, where you attack the source of the energy for which this device can compute. And we have investigated some problems and mitigations for that. So this brings me to the final slide. So This was a small menu of stuff we have done. And think of it as a business card as an invitation for contacting and having collaborations with us. So for instance, concerning fuzzing on software or testing for software, we are eager to see new classes of IoT software on which we can try our techniques. A particular effort we are starting is to look at software being tested in also the environment with the drivers and the hardware. This is hard to do in the real hardware, but on an emulation platform, you will be able to do that. And we are in progress to develop support for doing that. Concerning testing of protocol implementations, we are eager to test new interesting protocols. The progress now is in testing ADOC. We are developing infrastructure for that. For trusted execution environments, there is an implementation supporting it in Contiki NG. And if there is use cases for that, please approach us. And finally, with intermittent computing, we are trying to see how it can be placed on low-power reconfigurable hardware. So thank you very much for your attention. And
thank you very much.